Right, hello everybody. My name is Cristina Corti and I'm a PhD student at the University of Exeter. I'm part of a PhD program called WISE. And today I'm going to talk to you about getting towards an automated approach to quantify cliff retreat in 3D. Okay, so why an automated approach? I'm not going to bother talking to you about why I monitor cliff retreat because I'm sure most of you are aware of what's happening. But why bother automating? So depending on the spatial scale that we're looking at, if we want to carry out analysis at fairly large spatial scale, so beyond the local scale, then we might need to have a semi-automated or automated approach. Also, if we want to be able to quantify changes, not just over the longer term, but also in the short term. And if we want to remove any problems linked with manual digitizing, for example. So when somebody is tracing the position of the cliff top and the cliff toe, they are introducing some bias because it's their subjective judgment of whether the position of the cliff top is there or not. So with an automated approach, we kind of remove that problem. And also it's quite a tedious task. It can take quite a long amount of time, both to digitize the cliff top and the cliff toe, for example, but also to manually quantify the change. So I'm going to show you an example of a 2D change analysis for Sidmouth. So we're in the southwest of the UK and we are in this area of East Devon, and this is where Sidmouth is. So the cliffs to the east of Sidmouth have been retreating about a metre per year over the last 15 years or so. And this is a two-dimensional DM of difference between 2007 and 2018. You can see in red areas of erosion and in blue areas of accretion, where accretion is either material moving from the, so being deposited from the cliff onto the beach, or beach accretion, which you can see further down. Okay, well, let's take a step back. So this is an example of a LiDAR digital terrain model. Same area, you can see flat areas pretty well, but it's hard to make out what exactly the cliff face consists of. It's a bit smoothed out. This is a digital terrain model, so it has been filtered. There's no vegetation and no buildings. But there are better ways to visualize this data, for example, in 3D using the LiDAR point cloud. So for any of those of you who are not very familiar with LiDAR, the point cloud is the kind of first data product, and then this gets interpolated and you get a digital terrain model or digital surface model, depending on whether you filter or not filter. So this point cloud is color-coded by elevation, so you go in red higher ground and in blue lower ground. But what I'd like you to notice is the point density on the cliff face. So it is lower compared to the density on the cliff top or on the beach, but you can really kind of make out all the features that are present on the cliff face, including overhangs and notches. We can also use another attribute, the intensity attribute. This is stored when the aircraft flies over a certain section of coast by measuring the amount of energy that gets returned to the aircraft, and then we can color code this based on intensity values, so you can really see where vegetation is present, where buildings are, where water is, and where everything else is, so the beach, the cliff. We can also color code the point cloud by return number. So vegetation points will get multiple return numbers because the laser pulse will hit the canopy, for example, at the top, and then maybe hit a branch and then hit the ground. So you can see in kind of dark blue, the lower ground or the actual ground. Okay, but this is just a couple of things that we can visualize when we download the LiDAR point cloud. But what we can also do is something called segmentation. So this basically means classifying each individual point into cliff top, cliff face, and beach, or whatever class you might want to come up with, and perhaps vegetation and buildings, which you can see in blue here. So the way we do this is using an automated approach. Obviously, you wouldn't want to classify each individual point manually. And we can do this in Python or any other programming language that you choose. But in Python, there are quite a few libraries that let you compute features. These are, for example, the normal in the vertical direction and the standard deviation in the vertical direction again, that kind of let you separate the cliff face out from the rest. And then we can use something called dbScan, like clustering. This is a type of spatial clustering, and it kind of removes any points that have been wrongly classified and then puts them back in the right class. You might think, why do I care? Why is that relevant? Well, it becomes relevant when you're looking at changes in 3D. So a bit like your 2D difference model, where you compare two digital terrain models. But here we are doing a comparison point by point. So this is done in Cloud Compare using a plugin called M3C2. And you can see in red areas of erosion again, and in blue areas of accretion. Obviously, there's no accretion on the beach, on the cliffs. The only accretion you will see is either sediment deposition on the beach or vegetation growth. So knowing what points are vegetation and what points are not vegetation is kind of helpful when we want to judge where those changes have taken place. And I forgot to say that one of the advantages of using this tool in Cloud Compare is that you can call it from the command line, so then you can automate this calculation, for example, in Python again. So why aren't we using point cloud data more? There's a wealth of data that hasn't been used to its full potential yet. And I think this is probably because it comes in a bit of a weird format. This is LAS, or the compressed version, LAZ. And yeah, it's quite heavy. It's a bit heavier than your standard XYZ or ASCII file. And it takes a little bit longer to process. Software could be an issue if you're not very familiar with what software is available out there. But Cloud Compare is excellent for doing anything from visualizing the data to calculating attributes to calculating change in 3D, for example. Some of the problems I have encountered are, for example, in the segmentation. So classifying the cliff face, cliff top, and the beach. That sometimes proves to be a bit tricky if we have low density areas over the cliff face, which can be a case if the capture angle is not perfect. But you can also have a very steep cliff top, and this can cause to misclassification errors. Also, when you want to calculate volume, you still have to interpolate, be that to a mesh or a DEM, but you still need to interpolate to get an accurate estimate of a volume. So when I started my PhD, I set out to do some UAV flights. This is using a DJI Mavic 2 Pro drone. So this is a commercial drone. It's relatively low cost, about £1,500, and it's not a survey grade drone in any way. So I was about to start flying around March 2020, and then obviously the pandemic hit, and then I wasn't able to start doing any proper surveys until about September time. And by then it took a little while to figure out a methodology that would capture the cliffs, both in terms of facade scans. So get a nice picture of the cliff face, but also having another flights that would get an overview of the cliff top and the beach. We eventually found a good mapping software that kind of automates these missions so that we have enough overlap between all the photos that we take. And then we can put these photos in a software called Metashape that does that builds a 3D model using structure from motion. So drones are often seen as very exciting, and they are, because you can take awesome photos. You would never be able to survey something like that on foot, and you probably wouldn't get the detail from a plane. This is an example of a landslide at a sea town that took place in April 2021, and we went to survey shortly after. And I think it's just, yeah, the photos that you can take with a drone are pretty cool. But there are some downsides. So I forgot to say that the upsides are that you always go out on a really nice sunny day like this. There's no wind or little wind, no rain. Yeah, it's like perfect. Really nice conditions to go out on a survey. But the downsides are that when you want to go out and fly a drone, other people might want to go out and, for example, paraglide. So when we went back to Seatown in Dorset around August time, there was loads of paragliders because the wind was perfect for them to paraglide, and we couldn't fly the drone. So I'm now in contact with a few of the local paragliding clubs, and I know if it's going to be people out or not, because they need certain wind conditions, for example, south-southwesterly winds here in Seatown, in order to have enough lift. Anyway, we did manage to go back to Seatown in September. You can probably just about see that another section further west had failed. So we managed to capture that quite well. And again, we're going to put all the photos into the structure from motion software, which is going to build a nice 3D model. And this is an example of the first Seatown flight. So this is from April. And you can see how well Metashape has reconstructed the 3D point cloud for this area. Okay, before I move on to the next section, well, what I was going to say is that I feel like we are kind of traveling the world in 60 minutes, thanks to all the, well, at least the Southwest Coast, thanks to all the data that PCO collect and make freely available to anybody to use. This is just a drone, simple drone footage taken not far from Sidmouth. So this is just looking east of Solcombe Hill. And yeah, that wouldn't, well, not the drone data, but anything that we do with the LiDAR wouldn't be possible without PCO. I think we are one of the luckiest countries in the world to have so many sets of data. I think at Sidmouth we've got about 10 maybe. And I think that's pretty amazing. Okay, so I put here some of the resources, obviously PCO and CCO, but there's also another portal that I became aware of a couple of years ago called Open Topography, and they have lots of tutorials on how to work with point cloud data, but also they have a tool that works with the data that they have on their server without the need for you to download it, and it just does the 3D change analysis on the fly, basically on their server. And then I'm a big fan of open source software, so I use QGIS quite a lot for any 2D change analysis, but they've also got a 3D viewer now. And then Cloud Compare and Displaz is an excellent viewer. But also PLAS, that's an online viewer where you can upload your point cloud in LAS or LAS format, and you can extract sections and so on. So thank you very much for listening. I'm going to leave you with a picture of a nice landslide. This is not far from Torquay. And if I'm correct, there's a house on the, well, there was a house on the cliff top. This was sold at an auction, and the new owners weren't really aware of what they were buying into. And a few months after, when they turned up, their house was gone. So if you have any questions, you can email me, or feel free to follow me on social media. But if not, I look forward to the question and answer session on the 3rd of November. Thank you.